Welcome back to Calculus 2. This is the first video in Section 2. This is Section 2.1, Areas Between Curves. We're going to start off by looking at area of a region between two curves. Let's get a nice little picture. We have a blue shaded region, which we're calling capital A. We have a curve that's bounding A from above, and we have a curve that's bounding A from below. Let's name those. Above, let's term that curve y equal f of x, and below, let's term that curve y equal g of x. Come back, look at the shaded region. To the left, capital A is bounded by x equals 1, and to the right, capital A is bounded by x equals 2. Very nice. If we were to take everything underneath the curve y equal f of x, all the way down to the x-axis, we could compute that area with a definite integral, bounds of integration, little a up to little b, and integrand f of x. On the other hand, if we were to change the integrand from f to g, then that definite integral would give the red shaded region. The region that we're interested in is capital A, and thus capital A can be computed by taking the integral of f, producing a large area, and subtracting the integral of g, which produces a small area. Very nice. This looks like it's a two-step computation. First compute the big area, then compute the small area. But thanks to properties of integrals, we can combine this difference of two integrals as a single integral. Hey, very nice. Properties of integrals. Nice. Thus, our integrand is the output of f minus the output of g, which is the output of the function f minus g. Okay, so that's area between two curves. That essentially finishes this section, but it also provides a wonderful opportunity to take a look at this in a more formal fashion, and that's what we'll do right now. So, if we want to think more formally, the topic of this section is area between two curves. We've just written down a definite integral. In defining definite integrals, what do we use? We use Riemann sums. What does a Riemann sum look like? Yeah, a summation, I equal 1 to n, and then a height function and a base function. F at xi star, that's providing some height. Delta x, that's providing a base. What is height times base? That's the area of a rectangle. Okay, so let's try and reproduce this expression, but in the application of area between two curves. Okay, so we're back to looking at the curve for f, given by blue, the curve for g, given by red. And then we have a rectangle, which has been shaded. And if you look at the height of the rectangle, it's off to the left endpoint of the interval a to b. The output of f at A minus the output of G at A. Thus, this is using one single rectangle to approximate the area between F and G. Okay, we're going to watch a video, a little animation. Here's one rectangle. Let's look at more and more rectangles, and then observe that as we do that, we get better and better approximations, leading us to the conclusion that if we take a limit of this, as the number of rectangles goes out to infinity, that we get the exact area between F and G. All right, that's a familiar concept, taking a limit. Let's back up a little bit and work with a very small number of rectangles. And then again, observe that each rectangle sits above some subinterval of the large interval a to b, and that the height of the rectangle has been produced by the output of F at the left endpoint minus the output of G at the left endpoint. Let's go to an arbitrary rectangle. Output of F at the left endpoint minus the output of G at the left endpoint, providing the height. So each of these rectangles, of which there are n, each rectangle has a height of F at the left endpoint minus G at the left endpoint. That's the height of each rectangle, multiplied by the base of the rectangle. Looking at each of these rectangles, remember that our convention is to use regular partitions so that the base of each of these would be the same. Very good. Thus, we can recover the entire area between the curve of F and the curve of G over the interval a to b in this definite integral, which we have just argued is the limit of this Riemann sum. Very nice. So this sort of revisiting of a Riemann sum and constructing it anew is something that we've seen before in producing volume integrals. And here we've had another opportunity to employ such an argument. Excellent. Let's do an example. All right. We want to know the area between one curve and another curve over some given interval. The interval that's given to us is 0 to 1. And we know that the function e to the x produces larger values than the function x over this interval. Good. In other words, what we've done is we've identified the larger function f of x and the smaller function g of x. And as this question is asking for the area between those two functions over the given interval, we know to use the large function minus the small function as the integrand, and then the given interval providing the bounds of integration. Super. Each of these functions, e to the x and x, has a straightforward antiderivative. E to the x has e to the x as its antiderivative. X has x squared over 2. Thus, we can easily compute capital A, e to the 1 minus 1/2 times 1 squared. That difference, subtract away the difference of e to the 0 minus 1/2 times 0 squared. E to the 0 is 1. Combining with 1/2, we come up with our final answer. Fantastic. All right, your turn. Here are a couple of pairs of functions over two different closed intervals. Nice. So that was area between two curves. Let's next look at the case where a domain perhaps is not given to us, but rather two functions, for example, y equal x squared minus 3, nice parabola. This parabola will open upwards. That's one curve, and a second curve, y equal 1, that's just a horizontal line. So parabola opening up and a horizontal line, those two functions, as specified, will define a particular region. Nice. So where do these two curves cross? Well, when is y equal to y? So that requires that 1 equals x squared minus 3. Move the 3 to the other side. X squared needs to equal 4, or x is positive 2 or negative 2. Good. So that's going to provide bounds of integration. And then for the integrand, we know that we're going to use the large f as 1. And for the smaller function g, we'll use the parabola x squared minus 3. Very good. Set that up. The area between, the area determined by this region is given by the definite integral from negative 2 to positive 2 of large function f of x minus small function g of x. Having spent a few moments to produce the graph, we can see that for this graph and for this domain of integration, we can take advantage of the symmetry about the y-axis, cut the domain of integration instead of negative 2 to 2, take it as 0 to 2, and then double up the integral. I went ahead and combined the 1 and 3. Integrand is straightforward to evaluate. 4 goes to 4 times x. X squared goes to x cubed over 3. And we only have to consider plugging in the upper bound, since plugging in the lower bound would produce 0. Fantastic. So again, this is the case where the domain of integration was not provided. A region is bounded by some curves, and then we go and figure out the bounds of integration ourselves. Beautiful. All right, your turn. So here we have 3 different regions that are bounded by given curves. Find the area of the bounded region. Fantastic. Okay. So that's area between two curves. Next, let's talk about a complex region. And then after doing that, and related to that, we'll also consider integrating with respect to y. First, let's take the curve y equals 0, which is just the x-axis, the parabola y equals x squared, and the nice linear function, 3 over 2 minus x over 2. make a sketch of that. So the blue parabola is sketched, vertex at the origin. The linear function 3/2 minus 1/2 x is a line. Slope is -1/2. That's the red curve. And we had a third function, y equals 0, which is just the x-axis. Those three curves combine to bound a region. We've termed it capital A. So what's going on to make this a complex region is that as we set up our integral from 0 to 3, that the function f of x, bounding a from above, changes from being this parabola to being the linear function. And then along the way, where does that occur? That occurs at x equals 1. Quickly verify that. 3/2 minus 1/2 is 1, and 1 squared is 1. So indeed, it occurs at x equals 1. Well, what that means is that we'll have to compute the area a sub 1 and a sub 2. Add those two areas to get our desired answer, the area of capital A. All right. So you can apply your techniques that you already have to finding A1 and A2. And we'll come back and we'll look at what the answer is. But we're going to use this complex region to explore integration with respect to y. Okay, so let's come back to this region, capital A. And we want to look at this region and integrate with respect to y. Okay. So here we're looking at the two curves, y equal x squared, the parabola, and the linear, y equal 3/2 minus 1/2 x. And then for each of these equations, we have solved for x. Okay, so remember, the idea here is that we want to integrate with respect to y. So we're observing that this region, capital A, if we want to let y be the independent variable, then from what bound to what bound do we need to consider y's? And capital A only occurs, pick any point in capital A, and you're only going to have a y coordinate falling between 0 and 1. Okay, so that's going to be the bound of integration, or the interval of integration. Let's pick an arbitrary value between 0 and 1 on the y-axis. Pick something arbitrary. Now, for this particular y coordinate, this particular y value, highlight all of the points in capital A, in the region capital A, such that the y coordinate is this arbitrary value. Let's draw that in. Good. So every point on this horizontal line segment has y coordinate given by exactly this y value. And then on the line segment, I've highlighted the endpoints. Let's look at those x coordinates. Here are the x coordinates. And then you have one x coordinate to the right and one x coordinate to the left, or a large x value and a small x value. So, on what curve does the large x value come from? And on what curve does the small x value come from? That's what we want to look at right now. So the large x value is coming from the linear function. So write that out, that the large x value is given by 3 minus 2 times this arbitrary y value. That's for the large x value. On the other hand, at the other endpoint of the line segment, the small x value is occurring on the parabola. We already know the y value. We're trying to figure out the x value. So we take the parabola y equals x squared, solve it for x, and come up that the small x value is given by radical y. Very nice. So this y value is going to vary from 0 up to 1, our bounds of integration. And then for each y value, we want to consider the large coordinate minus the small coordinate. In other words, the f minus the g, in order to set up the integrand. Let's go ahead and do that. We'll take the large x-coordinate, subtract away the small x-coordinate, use that as the integrand. These x's, these outputs, big X, small x, are given in terms of y. Thus, we're setting up our integral as an integral with respect to y. And if we want it to be a definite integral, we have to say where the y begins and where the y ends. And we know that this region A has y values corresponding only for y's from 0 up to 1. Bounds of integration, 0 to 1. Beautiful. Look at the integrand. The integrand is simple enough. Elementary integrals. Evaluating out, as you found already, this region has area 4/3 square units. Fantastic. All right. One last thing to consider. Suppose that we have a region that looks like this. Then start thinking about vertical lines or horizontal lines. In other words, does this region suggest we integrate with respect to x, i.e. vertical lines? Or should we instead consider horizontal lines and integrate with respect to y? Well, if we look at x's, negative and close to 0, that a vertical line would have a strange interaction with the region. It'd enter, exit, but then enter again. Whereas if you consider any horizontal line, like the x-axis, that following a horizontal line, you enter and exit. That's it. Horizontal line, you enter and then exit. So, because of that, we're going to integrate with respect to y. Beautiful. Let's begin then by considering bounds of integration for y, looking at all the shaded region. Where does y begin and where does it end? First, let's write down what these curves are. Note that they're expressed out as functions of y. So x is isolated, which is what we need if we want to integrate with respect to y. We need x to be solved for. And then we have 3 points of intersection for these two curves, the red curve and the blue curve. Where will that intersection occur? Oh, take a look. 3y cubed minus 2y squared. We can factor off a y squared, and we'd have y squared product 3y minus 2. Aha, very helpful. When is 3y minus 2 equal to 0? This point here, 2 over 3. So this point has coordinates x equals 0, y equal 2/3. If we consider y equaling anything else, then 3y minus 2 is not 0. We'd come up with the equation y squared equals 2. So if y is not 2/3, we can divide both sides by 3y minus 2 and come up with y squared equals 2, meaning that y is plus or minus 1. Good. So we have the coordinates -5, -1, 1, 1, and 0, 2/3. In other words, our bounds of integration for this region will be from -1 to 2/3, and then again from 2/3 up to 1. Very good. Let's start with the region capital A sub 1. So we know that that region A sub 1 occurs for y values between -1 and 2/3. So those are the bounds of integration. And taking a horizontal line, moving from left to right, that you would enter the region on the blue linear curve, and you would exit the region along the red cubic curve. Thus, we would take the cubic function and subtract the linear function for our integrand. Very good. Focus in on the other shaded region, and the roles of large x and small x have changed. So this second shaded region, let's call it A sub 2. And then we can compute out A sub 2 as the definite integral from 2/3 up to 1. Enter in from the left, that's the small x value. Exit out on the right, that's the large x value. Take the linear x and subtract the cubic x. Beautiful. Evaluating these out, summing A1 and A2, we come up with a definite value. Sweet. Now it's your turn to have a little fun. Determine the area of the region bounded. Well, you have 4 curves and you have a couple of regions. And then you want to consider, is it going to be beneficial to integrate with respect to y or with respect to x? Have fun. That finishes up this first video in section 2. Thanks so much for watching. See you on the next one.